So this is an introduction to splines. Splines play a central role in computer software, computer graphics and games. Whenever you see smooth motion paths, a curved user interface, camera gliding through a scene, character following non-linear routes, or even animations, splines are usually behind it. Most modern game engines and tools provide built-in spline systems, which can make them feel like black boxes that simply produce the curves on demand. However, to use the splines effectively, it's useful to know how they work, how they're defined and constructed and evaluated, rather than just purely relying on the engine's behavior. So over the next few slides, we'll take a look at some of the most common splines and start to understand how they're created. So while we're looking at splines, it may seem odd to start with a line, although a line is technically a first degree spline. It's the simplest form of spline, that is a straight line between 2 points. A line can be classed as a straight path that extends to infinity in both directions. Quite often when we refer to lines, we consider them what we would call a line segment, that is 2 points and the line between them. Point 1 is the start, point 2 is the end, although as you can imagine that line could continue off into infinity in both directions. So most people have heard of the slope intercept form, y equals mx plus c. It's one of the most common methods taught at schools. M is the gradient, so given two unique points on the line, we can calculate the gradient. Once we have the gradient, we can then calculate c, which is the y-intercept, as shown here. But this has a distinct problem. When x2 equals x1, we end up with a divide by 0 for the gradient, so a vertical line has a gradient of 0. This isn't too hard to code around. We have to have special cases, and special cases are usually a bit of a pain when programming, so there are other ways we can look into this. Another form of line formula we can look at is the point slope form. It's very similar to the y equals mx plus c form. We still need the gradient calculated in the same way, so we still have the same issues of x2 equal x1, which means we still have a divide by 0. With both of these, to calculate more points along the line, we can take an offset along the x-axis, call it d, and the offset on the y-axis simply becomes md. So we can calculate new points based on this. While this is fine, if we want to move a specific distance along the line, it requires additional steps to calculate the offsets that are needed. So none of these are ideal. So a better way to look at lines is with a technique called parametric lines. The equations are here. T is a parameter which is the distance along the line. P1 and P2 are points on the line. Quite commonly, if it's a line segment, that would be the start and the end point of the line segment. We can evaluate any point on the line in 2D simply by these equations here. Again, x1 and y1 are your start point, x2, y2 are the end point, and t, which is the same in both equations, is how far along the line we are. If you want to extend this to 3D, we simply calculate z in exactly the same way. When t is 0, the calculation would provide p as p1, so that is at t0 we are at the start point. When t equals 1, p equals p2, so we're at the end point. T can be less than 0 or it can be greater than 1. If it's less than 0, we are extending off before the start point, and if it's greater than 1, we're extending past the end point, carrying on that infinite line. We can have a look at this and see how it works with a quick example. If we take a look at this example, we can see here we've got 2 points, A and B. The line can extend off as shown in both directions. At the moment t is 0, so our point P is exactly the same as A. As we progress along the values of t, so P moves over until t is equal to 1, at which point we're on B. As we said, we can then move t greater than 1 or t less than 0 to carry on this line in infinite directions. Hopefully you can see how this would be useful to allow camera movements. If t was often used as a time parameter, we can define 2 points, place the camera at the start, and as the game is running, so this camera would then automatically be able to move along. So now we know how to handle parametric lines. We can start to actually look at splines. As I say, lines are a type of spline, but most people consider a spline as a curve that passes through or near sets of points. There's various different types of splines. A few examples are quadratic Bézier, cubic Bézier, hermit, Catmull-Rom, and there are more. They all tend to follow very similar mathematics. Quite often it's just how we define the control points, which we will look into shortly. So we'll start looking at a quadratic Bézier spline. These are one of the simplest splines. It's built from 3 points. We have A, start point, B, the control point, and C, the end point. The spline passes through the start and end points, and the single control point is used for just how much of a curve there is. So, as I say, splines are effectively built up from parametric lines. So how do we use parametric lines when we have 3 individual points? So here again, we can see our example. We have 3 points now. We have A, B, and C. We calculate a value of t. This is a single value of t for both these lines. As t is 0, we calculate a parametric line going from A to B, and again, a line going from B to C. So as we move along, so these 2 points, as expected, move to the end of the line segments. So as we saw with that example, we're moving 2 parametric lines at the same time, but using a single value for t as the parameter on both. So P1 is moving from A to B based on the t parameter. P2 is moving from B to C, again based on the t parameter. So we now have 2 points, P1 and P2, that we've calculated. We can use these 2 new points as a new parametric line going between P1 and P2, as shown here. So let's see how that would look in practice. So again, we have our example here with our 2 lines, A to B, B to C. We've now got this green dotted line, which is our new line, which is going from the point we calculate between A to B and the point we calculate from B to C. So now, as we step along the value of t, you'll see the green line moves to carry on being between P1 and P2, and P3 is moving along between these 2 points at the same time. Some of you may have seen, if you watch the point that moves between P1 and P2, as we move, so it draws a curve as it moves along between T0 and T1. The green line, the solid green line here, shows you the path that P3 has taken as we've stepped these lines between T of 0 and T of 1. So as we saw with the quadratic Bézier curve, P3 is actually tracing a curve between A and C. B is defining how much of a curve it is. Now, there is a little bit of maths behind this. It's fairly straightforward, but I recommend you take the time to go through it, do this maths yourself as well, just to make sure you fully understand it. As I said, I'm going to use the slightly different version of the equation, but P1 is calculated based on t as the point moving between A to B. P2, again, as I was saying, but this time we're moving from B to C. What we can now do is we can now calculate P2 minus P1 in terms of A, B, and C. So P2 minus P1, we have a value for P2, we have a value for P1. We multiply out the brackets, collect terms, and get to this point here. So we've now got a value for P2 and P1 based on our start point, end point, and control point. So using the value that we calculate, P2 minus P1 and P1 itself, we can substitute these into our equation for P3, as shown here. Again, we multiply out brackets, collect like terms, and we end up with this equation here. So now what we actually have is we know the point P3 based solely on our start point, end point, control point, and the single value of t. It's called a quadratic Bézier spline, although I've shown it here, it can be represented in quadratic form. That is, we have a t squared term, a t term, and a constant term. So drawing the curve, now we can calculate any point along that curve based on a single value t and the 3 points. To draw the curve, we simply step incrementally along the curve. So we go from 0 to 1 with t. Depending on how small a steps you take depends on how smooth your curve will be. So you could step 0.1 and you'd have 10 small line segments. We'd draw from t0 to t0.1. We could draw another line segment from t0.1 to 0.2. And this will represent the curve. As I say, the smaller steps you make, the smoother your curve will look. So if we go back to this example, this is the quadratic curve. We can see the quadratic curve being drawn as we move t between 0 and 1. What we can also do is we can show, we can move our start and end point, and we can see what the control point does as we bring it down more in line with A and C. So the curve becomes flatter. As we pull it up, so it becomes steeper. We can make it lean to the left and right. And this is a quadratic curve. What we'll do next is we'll look at cubic curves that have 2 control points and allow some more movement. So now we've looked at quadratic Bézier, we'll look at cubic Bézier. These tend to be more common. They're the basis more for the Catmull-Rom and the Hermit splines and such like. They extend the quadratic spline. That is, rather than having 3 points, we actually have 4, which gives us 3 parametric lines. Again, we have a start point, usually A, we have a control point B, and we have a control point C and the end point D. So what we've done is we've added an additional control point. So now we have 3 parametric lines, A to B, B to C, C to D. Again, we use a single parameter for T. Very similar to quadratic, we calculate a point moving along the line between A and B. We calculate a point 2 between B and C. We also now have the third line, so we calculate P3 this time between C and D. Remember, A is the start and D is the end. B and C now are both control points. So this gives us 3 points. Now we have 3 points. We can create 2 additional parametric lines between these. So we have P4 is a parametric line between P1 and P2, and P5 is a parametric line between P2 and P3. Based on T, again, T is exactly the same value in all these equations. And now we've got these 2 points, similar to quadratic, we can simply calculate the final point as a parametric line P6 between points P5 and P4. So let's have a look how that looks in an example. We can show this visually again. So we have A, B, C, and D. A would be our start point, D would be our end point, and we can again move T across. As you can see, as we move T, so we are calculating P1 and P2, P2 and P3. These then produce a new point, P4 and 5, and finally we can calculate P6 along this. As you can see, as this curves, we pass through A and D, and B and C becomes control points. If we move these, you can see how they can be used to adjust the style of curve that we see. So the cubic Bézier spline the maths is very similar to the quadratic. There's, as you can imagine, there's more points to calculate, there's more terms to collect. I'm not going to go through individual steps here. I strongly recommend you do go through the maths yourself just to prove it. But once you've multiplied everything out, collected all like terms, you'll end up with a cubic equation that will equate to this. This is a cubic. We have the t cubed term, the t squared term, the t term, and the constant. This produces the curves that we saw. Now, once we've got cubic Bézier splines, obviously one spline is great. when we use them in software, we can actually chain these together to allow us to produce various different effects depending on what we need. To do this, our first spline is, as we saw, A to D, A being the start point, D being the end point, and our two control points. The next spline, D, the end point of the first spline, would become point A, the start of the second spline. We'd have two more control points and have another end point. This is how the curve carries on. If we show this an example, we'll see how this works in practice. So as we can see, we have two cubic splines. Point D is shared. It's the end of the first cubic spline and the start of the second cubic spline. As we move T from 0 to 1, we move along the first spline. And as we move from 1 to 2, move along the second spline. Obviously, this is just showing the two-step ones. To actually calculate the points between D and G, you would still only use a T value of 0 to 1 because it's calculating from the start to the end of the particular line segment. The fact it's between 1 and 2 is because it's the second line segment. These are still control point B and C are control points for the first spline. E and F become the control points for the second spline. Now, as we mentioned, the continuity of this spline is such that we can create sharp right angle corners. We can break that smooth curve feeling because we are not enforcing continuity. If we put the points fairly much on a point C to E in a straight line, then we will get a nice smooth transition between those curves. We don't always want that. Sometimes we do want to have the harsh curves. This is why understanding how these work, you can see why certain features are within spline systems. Here's another example of the two splines. This time we've actually enforced a constraint between C, D and E, so they're always in a straight line. D is always the midpoint between them. As you can see with this, it does mean we keep a much smoother curve all the time. This is keeping continuity. Continuity of splines is classed as C0, C1, C2, etc. This is only keeping continuity of effectively the visual, the tangent of the curves. Then you could get the form where if you're moving through these all at the same rate, so stepping through at say 0.01 along T, you could find that the movement, if you were using it a camera to follow the speed, could alter as it came into the second spline. There are ways of enforcing this as well, which is the next level of continuity. This is the simplest one where we literally just ensure that the points C, D and E are all on a straight line and effectively equidistant. Quite often this is enough. The level of the maths starts to increase as we start to look at new continuity, but for an introduction to splines, we'll just look at this. We'll just introduce this concept here, just in case you want to carry on a smooth spline. We'll also quickly look at an example of how splines can be used in the games industry to quickly help produce assets and features within the game. So let's look at how to use splines in a game. We imagine we're going to do a simple top-down racing car game and we want to create some levels, some tracks for the cars to go around. So the first thing we can come in is in Unity is we can just ask it to draw some splines. So I'm just going to lay out a track, something that look a bit like a racetrack for the cars to go around. Obviously it needs to loop, so you can keep doing laps. Now what we want to do is we want to take this spline, and to make our actual racetrack, there is a function called spline extrude. Now what this does is it effectively takes a small box and stretch it around your spline, giving us a nice, slightly thicker racetrack. Now at the moment it's looking a bit boring, it's just grey, so I've got a texture here that I've already used, created. It's a little section of road. So if I now create a new material, I'm just going to, for ease, use an unlit textured. I'll drop my road onto it. I can then come back to the spline and I can ask it to use this material instead of the default one. And you see we've now got a road. What you'll notice there's a little bit of road at the start and not anywhere else. This is because what we need to do is, as it's repeating this texture all the way around, we need to make sure it's on repeat mode. And there we go. We now have a racetrack. Because it's a spline, at any point, if we want to tweak it, we can come in, use up here, the spline editor tool. We'll see our little spline points and we can pull them around to change the look. What you will notice is these are on auto mode. We can go to Bézier and change these. What you'll notice then is we've got our two control points. If you remember from the examples we had earlier, these are two of the control points. This is why if we make them so they're not continuous, it looks fairly horrible. You can get some very horrible sort of disjoints. Not really what you want. So auto is often the best mode for using it in here, but you can understand why these are what they are and how they're needed. But yep, so that allows you to edit the splines, and as you can imagine, you can quite easily draw more and more splines, lots of different levels, and you're creating a very quick level for you to test. The other thing you can use, as you've got this spline going around here, if you wanted AI cars to drive around the track, all you need to do is have a value which goes along the spline, calculating the point, and based on the distance you've gone along the spline, calculate the point, and the AI can simply follow this point. You can add variations on distance from the point. You can take a point further ahead, work out how much it's in the direction you're moving, to calculate whether or not a sharp corners allow you to add braking into the AI. It's all very simple, all based off the spline. So as soon as you calculate a new track, draw a new track with a new spline, all the AI can automatically follow it again. Obviously, there's a lot more you can add and a lot more to get complicated looking games, but for a simple system, it's straightforward and allows you to get going quite well. So yeah, hopefully that gives you a bit of an insight into what splines are, why we use them, how they can be used. If anyone wants to put any comments, I'll try and reply to them. If there's anything you want me to go in more detail, or if there's anything you want me to look at instead, then please drop me a message.